Hello and welcome to the video. Now imagine a group of friends are playing a game that involves rolling a standard 6-faced die on a table which is covered with black and white tablecloth. A friend notices that in approximately 1/3 of the tosses, the die lands within a single stripe. What we're going to do is develop a mathematical model that explains this observation, taking into consideration that the width of each stripe is about twice the side length of the die. Now, our initial assumptions are 1. All stripes are identical. With this, we can consider the die landing on only one stripe, so the table's width is negligible, i.e. if it lands on the table, it will either land fully within any stripe or not, for example, lying between two stripes. 2. Each face of the die is a perfect square, and 3. The die is thrown randomly. Pretty standard trivial stuff. Now, since the width of the stripe is double the width of the die, we can label the width as 2, and the length of the die as 1. For the die to be within the stripe, we need to think about the maximum horizontal distance between the furthest left-hand point of the die and the furthest right-hand point of the die. We can call this length L. Now when the die is horizontal, the length L is 1, as shown in our previous example. But when we subdue the die to an angle theta to the horizontal, we have two similar triangles, and can calculate L to be sine theta plus cos theta using trigonometric identities, where theta is a continuous random variable. The probability of any length L for the die to be fully within the stripe is 2 minus L all over 2, as this gives the distance the die could move to the right, assuming the die starts furthest left it could be before the die extends the boundaries, i.e. the die lands in the next stripe too. Rearranging for theta, this then gives the probability for the die to land within the stripe as 2 minus sine theta plus cos theta all over 2, and because you're working with continuous random variables, you can use this as a probability density function to integrate. Now, we need to consider the range of angles that theta can take. Since the die is a perfect square on its faces, for each pi over 2 turns, the instances of the length L are going to repeat periodically, so we can take the lower and upper limits of integrating our density function as 0 and pi over 2 respectively. However, this integral will give a value greater than 1, which statistically is impossible as we are working with a probability density function. We need to divide by pi over 2 to find the mean probability for any angle theta between 0 and pi over 2. This is equivalent to multiplying the integral by 2 over pi, and so we can now find the probability for any L of the die landing within the stripe. If you plug this into a calculator, the integral gives the value of 0.363 ... which is approximately a third, and that is the result we are trying to find. Thank you for watching our video. We hope you've enjoyed it.